I'm the lead developer from Chemistry Education, and I'm part of the Wolfram Alpha Chemistry team. And today, I would like to share with you the new things that have been going on in chemical education since we met last year at the WTC. So our tools for chemistry are ever growing. We have a new one that I'll be talking about this year that you probably already heard about in other presentations so far, the Wolfram Notebook Assistant. This builds on the Wolfram GPT and Wolfram Alpha, and of course sits on top of Wolfram Language. These four things in the top are where my talk will focus about today. But just a reminder, if you're new to us, we have virtual chemistry labs. We have the Wolfram Alpha Notebook Edition for multi-query alpha interactions and to train chemists how to do coding. We have demonstrations, which you can build your curriculum around in different classroom activities or learning space activities, possibly even lab activities. These saw quite a lot of use during the pandemic. We have a growing example repository with examples of how to do complex chemistry problems, both research and school-oriented. Our function repository has add-on programs, well, not programs, functions that you can use in your own work to flesh out your programming. We also have a larger collection of functions in the paclet repository, and the data repository is all available to pull right in and do calculations yourself. So over the last year, we've been rather busy, actually, talking about chemistry and talking about what you can use the Wolfram language to help do good chemistry, whether you're teaching or you're doing research. We started off by talking out at Parkland College here in Illinois. Then I was invited to speak in Chem 213 at Stevenson University, talking about AI and how it can be used in the chemistry curriculum and your chemistry research. I got to speak to them just recently last month, so that was, I got to talk to in that class twice. We also were at the spring and fall ACS meetings. So the American Chemical Society meets twice a year, and we were there presenting the summer research program at Wolfram's WSRP. We were speaking there and talking again about some cutting edge research at Hopkins and also some uses of AI. The ACID series we were invited to, which is a summer series for chemical science undergraduates. And in all of these conversations, we got to really know quite a few different chemists, hear how things are going, get feedback of what we should be working on. And we are very excited that we were able to be at the exposition at the fall ACS meeting in Washington, DC. So there's John and myself and Ashley, and Heidi is taking the photo, but we got to talk to well over 300 chemists, had in-detail conversations about our tools and what they are trying to do, and we made a lot of new friends, so we were very excited to be there, and the feedback has been very wonderful and critical to making decisions on where we should go next. So after going to the ACS meetings and different presentation venues, we were involved with the summer programs. You may not be aware of it, but we have two programs during the summer, the WSS, which is our adult program for anyone that's 18 years and older, and our WSRP for those that are 18 or that are younger than 18. And these programs have been going on for quite some time. I have data here showing from 2017 all the way up to this year. And as you can see, the number of chemistry projects in these two programs has been steadily increasing. In fact, we're really excited how it's taken off since 23. And since 23, 24, and 25, the last 2 years at the WSRP, a full 15% of the student projects were chemistry, which is just really amazing and terribly exciting. So we've been very excited about all the interest and how we can introduce students at the high school level and other levels to chemistry and possibly, teach them chemistry through coding. So I'd like to show some of the things that they were doing. Stephen spoke about this a bit in his keynote, and so here are the examples from chemistry. So we had, Eileen was working on metal interactions with molecules that are in the polysaccharide coating around the capsule, excuse me, around Cryptococcus neoformans. Arnie looked at insulin dosing over time and seeing how the kinetics of that were going. Andreas looked at mineral flow and had a very, very cool fluid dynamic flow as they were looking for where the formation of minerals occurred. Max looked at the interleukin protein binding using the tools that we have currently to do rudimentary protein binding studies and investigations. Karavan did the Thomson problem. And for those that may not remember, the Thomson problem looks at how charges are spread out over a surface. And that is the underpinnings for VSEPR theory in chemistry. So we were very excited to hear about his efforts there. Vikrant was looking at functional groups. Those that have taken any sort of organic chemistry course know that the organic chemistry community thinks about molecules as composed of various functional groups along a backbone. And Vikrant was writing software to identify those groups and automatically when you pass in a molecule. So he was building up a library of functional groups and code to identify it. Sarah was working on DNA knot dynamics. So these are knots that were formed by actual DNA molecules. Sarim was looking at tumor immune interactions with chemotherapy using differential equations. UT was looking at cloud seeding and specifically the surface water interactions in cloud seeding and looking at it from a discrete molecular point of view to complement experimental work that she had done. Jasmine got to play with the protein folding, the localized protein folding when she was looking at sickle cell anemia genetic mutations. Advika was one of the very first users of the quantum chemistry package, which I'll talk about at the end of my talk. And you may have heard about in Stephen's keynote. But one of the things that she was looking at was molecular orbitals and diatomic molecules. These are beautiful pictures, and we'll talk a little bit more about this later. And lastly, Ian was looking at molecular dynamics trajectories and characterizations in spatial temporal regimes with our tools. And so we were very excited about all of these projects and look forward to next year's crop of students who I believe for both programs, the application process should be beginning either currently or imminently in the next couple of weeks. So as I was saying, when we were traveling, giving talks throughout the country, the one major topic, not surprisingly, is generative AI. And Wolfram has been involved with generative AI since the start. We had a plugin model for ChatGPT and then have built out tools since then. Chemistry, like many fields, has slowly been adopting generative AI and figuring out where this can work in their classroom and in their research labs. And the most recent article that just came out in Nature Reviews Chem, actually just a few weeks ago, was an opinion article that very clearly stated a strong opinion that, the title was "Don't Let Generative AI Shape How We See Chemistry." Remember that chemistry, for those of you that may not be actively practicing chemists, is very much driven by visualization, since we can't, unlike some other fields, just pick up the objects that we're interested in. Molecules are too small to just visually inspect. And so we have a lot of models of how we represent them on the screen and in 3D, since we can't just pick them up by our hands. And so that sort of rendering, the sort of visualizations are really a source of error when it comes to modern generative AI. And this is something that I've been talking about for about 2 years now. So this is not a new thing, but as the article here goes about, here we've got an example of the periodic table from ChatGPT, Copilot, and Gemini. And I apologize if my screen isn't big enough for you to see all the small details, but here, for example, there's an extra row. There's bits missing. The actinides are completely missing from Gemini. And things are amiss over here as well in the ChatGPT response because they're making it up as they go. which isn't good when you're talking about chemistry. They don't get much better for discrete molecules. Copilot does get benzene right. ChatGPT sticks extra carbons there, and Google, well, yeah. Caffeine turns out to be a challenge for everyone, although it's often the molecule that's fueling a lot of research in computer science and definitely chemistry. This is not the structure that you should get, and these are just wrong. And the concern in the article is that if you're in a learning environment and you're a student, you may not have enough chemical savviness to know and catch that this is not the right structure for the molecule. And that's a problem. But it turns out that Wolfram GPT, which is the modern evolution of our plugin for ChatGPT, solves that. If you give deterministic tools, such as the Wolfram Cloud or Wolfram Alpha, then you can nail down the results for structure. But of course, this comes with a caveat that if the generative AI, whether it's Google's or OpenAI's or somebody else's, that is still a probabilistic model, and it may choose, like a human student, to not use the tool that you've given it. And if it does that, then all bets are off. But when it does use a tool, here's an output from using the Wolfram GPT. So this is part of the OpenAI collection of GPTs. What you see is you get a reliable periodic table from Wolfram Alpha. And you get this every time you ask the question that you need a periodic table, it'll come back out. Same with benzene. And not only can they get the 2D structure right, but we can get the 3D structure right as well. Now, maybe the sizing is a little bit too big, but at least we're not lying to the student. And as well, we get caffeine quite correct. So if you're going to, use generative AI in a learning space, you've got to make sure that you're getting around this chemical structure problem. The evolution of Wolfram GPT, while this has been very useful in the chemical sciences for a year and a half, 2 years now, we'd like to do better. As I mentioned, here's a 2D picture of a 3D rotatable object, and it's really big. Maybe we don't want it quite that big. To get that level of control, then we can move into the next layer of generative AI that we think will be taking chemistry by storm, if you will, is the Wolfram Notebook Assistant. And this is where you can now embed all the components of the Wolfram GPT, but in a notebook, and give it access to more things, as you possibly have heard about. And so by way of showing this, let me show a couple examples here. So we'll start with Lewis symbols and atomic orbital filling. Lewis symbols are a way that we pick 2D representation of the electrons in a particular element. And so we, posed a question. I'm not going to run this live just to make sure that we get through everything. But, I said, hey, I'm learning about Lewis structures. I'm confused. Many students are. Can you show me what they are for carbon and explain what's going on? And so here, what's happened is that in addition to getting the same sort of responses that you would from Wolfram GPT, it can go off and run our code. And the chemistry team built a new function called the Lewis symbol. I encourage you to check it out. It's very cool. And it'll spit back then the Lewis symbol for carbon. And it has the 4 carbon valence electrons, spread around it. And then, of course, you get the usual good text description of what's going on. Well, the follow-up question is that this picture doesn't quite agree if you know something about quantum mechanics. You would expect that 2 of those electrons would be paired, and then 2 of them would be in separate orbitals following Hund's rule. And so, why is that the case? Well, we get a good explanation, but then you can go back and ask, and because the large language model now has access to other tools inside of our Wolfram ecosystem, it can go rerun that same code and change how the electrons are filled following a quantum model rather than a classical model. And then we get the anticipated structure that would also be returned by Wolfram Alpha. So again, here we're getting more in-depth interactions. And if we move on to, do I need to? Well, that's unfortunate. I wonder if I have, let's see, that should not be grayed out. Oh, well. We'll come back to that. That was just going to show the molecule view function that was called by the large language model to show 2D and 3D structures side by side. And while that's very helpful, the same idea here is that now when you've moved from the Wolfram GPT back over here where we had static images to the Notebook Assistant, now we can get results that are fully rotatable, which is much more useful if you're really truly interacting with the LLM to help digest structural difference and different functional group motifs and really dig into the chemistry of the molecule rather than just having a full picture. And as you know, as we see below, you can, once you have those images right next to the descriptions of what's being conveyed and what's not being conveyed, now you can interact with it. And of course, you can also, if you wanted to, make this bigger. And same with all of those. So that sort of interactivity you don't get in the Wolfram GPT or any other chat GPT variant, but you do in the Wolfram Notebook Assistant. And I think this is going to be quite revolutionary for chemistry instruction. Well, what makes part of this possible is that we have a deterministic AI on the back end, which is more commonly known as Wolfram Alpha. And so let me walk you through some of the things that we've been adding over the last year. I apologize in advance, the font on here rendered a bit small, so please grab the notebook from the cloud and have a local version of it so that you can see it a little bit bigger. But we have for a while had aqueous phase parsing. We can grab that in the all the aggregation states. We implemented all of those last year. And for ionic reactions like this, where you have salts exchanging ions, you would get the net ionic equation, total ionic equation, spectator ions, if you highlighted and indicated that the species were aqueous. Well, it turns out that you should be able to get that if you're working in media that is other than water. So if your solvent is something else and the salt is dissolved, well then the same results should come out. And so we fixed the results, and now if you just denote that something is in solution, not necessarily aqueous solution, and that it's a salt, we will then return the right things for the ionic equation results. We were also working on overhauling and expanding the empirical formula engine. And to that end, we now fix some of the edge cases that we didn't do before, and more importantly, return useful results to users who might have inadvertently made a mistake. Here's a case where the student has given 110% composition, which, the percent composition should only add up to 100. And so you get a useful message back to the user that hopefully helps students guide in both using our tools and working their problems. Also, if they inadvertently have a sign error that something is negative, or they have a 0 value for one of the components in the molecule, that gets now flagged as well. And these results, of course, are then accessible to any AIs that are using the Wolfram Alpha as a deterministic agent. We've also been expanding the step-by-step content. It's an ongoing effort. We really want to get into equilibrium problems, and as anyone has known, you've got to do concentration conversions potentially there. And so we started with the mass-based concentrations and did conversions. So here we can go from molality to mass percent. We've been able to do that calculation for a while, but now we have step-by-steps for that. And just as a reminder, if you're passing in numbers with error bars, those are propagated through correctly. And so here we've got a molal going to mass percent. So we move to SI units, make the appropriate assumption of 1 kilogram, figure out the number of moles of solute, and then go for the mass of solute, because it's a mass-based concentration unit. So then we need the mass of solution, and we divide those by each other and get the ratio, and then we have the mass percent. We can go the other way from mass percent to molal. I won't show you the step-by-steps. It's basically the same detail. We can also move from either of those two over to the units preferred by the analytical environmental communities, parts per million, parts per billion, parts per trillion. And you can see here, 30 parts per million really is an incredibly small molality. And so you can understand why there's a change in new units to parts per million, parts per billion. But that is all now fully supported. We expanded our support for Lewis dot structures and valence electrons and Aufbau diagrams. So now we have what we had always had, the Lewis dot structures or the Lewis symbols for ions. This is now the same code as you can get access to in the Wolfram function repository entry Lewis symbol. But now we can explain the number of valence electrons and the Aufbau diagram, which meant that we had to upgrade the engine underneath to more succinctly pick out non-Aufbau structure or non-Aufbau diagrams that occur for some of these species. And so that is now all generalized and much more robust. We also have some more errors, messages coming out. For example, if you ask about valence electron count for helium 2+, well, there's no electrons, and so you get a message about that. The new bit that we're quite excited about is we're working in bonds to try and flesh out the AP chemistry curriculum. So bond polarity is something that's there, and the corresponding bond types. So in the bond polarity, this is where you look at the electronegativity of each of the elements in the bond, and then you take the difference in the absolute value of that to give a magnitude of the polarity. And that polarity then allows you to, using a general guide, determine if this is a covalent, polar covalent, or ionic bond. Those are the three primary types of bonds that one can have. So we're excited about that result. We've also expanded our calculators. They're now up to 75 different calculators, all with step-by-step support. And then the new one that we're very excited about that you might have heard about this morning in the step-by-step get-together, the Clapeyron equation and the Clausius-Clapeyron equation. These were two critical pieces that were missing for both the Gen Chem and the, well, Clausius-Clapeyron in Gen Chem, Clapeyron in physical chemistry. And now we have full derivations at that, so that if you're curious about where the equation came from, or you're in an upper level course where you might need the derivation to modify and derive a specific version of the equation for your particular problem case, we walk you through all of that. And what's nice about building on the stack of technology that we have in step-by-step is that when we do an integral, we can, this shows you the Clapeyron derivation, and then we're building on it for Clausius. But when you're going down and doing integrals, we can click out and link to the step-by-steps for doing those integrals. Since, chemists might not always have the strongest math background, we have the resources right there to explain it. What I'd like to spend the last bit of my talk going over is the new quantum chemistry paclet that you may have heard of. We're very excited about this, and the paclet debuted this summer, and our summer program students worked with it. It'll be rolled into version 15 as was demonstrated in the keynote. But you can start playing with it now if you'd like. Just do a paclet install and then needs the quantum chemistry paclet. And so for my example, I'm going to build a carbon dioxide molecule. And I'm going to use the molecule, carbon dioxide, build it from scratch. And then, we can see here that if you look at the bond lengths, the two CO double bonds are 1.4 angstroms each. And just to keep track, the total molecule has 22 electrons in it. That'll become important in a bit, so don't forget 22. Now, you may not have run a quantum chemistry calculation before, but I have. So let me walk you through your first quantum chemistry calculation in Wolfram Language. When you start with a molecule like our carbon dioxide that we built before, we're moving on a potential energy surface, specifically the Born-Oppenheimer potential energy surface. So you need to optimize and find the lowest ground state geometry, in this case in the gas phase, for that structure. Why do you need to do that? Well, that's a whole nother quantum chemistry course that we could happily do. But the bottom line is that unless you're at a stationary point on the potential energy surface, the computed values don't match reality. So now that we've done the calculation, and again, we're doing it at the Hartree-Fock level with a very small minimum basis set, not publishable for quality purposes, but great for education situations and for short talks at a WTC. We can then extract the molecule out with all of its coordinates and see, here's the structure, again, rotatable in a nice notebook 3D space. And we just list that the point group is d infinity h, which is what you'd expect for a linear molecule. And the reason that we did the optimization is really shown here. The top row are the bonds that we started with, 1.4 angstroms. After optimization at the Hartree-Fock level, they come down to 1.18. That's a little bit different from gas phase experimental. I think we're a little longer, but we can improve those values by changing the model chemistry. But for what we're about today is we're curious about the bonding in this molecule. And so the number of molecular orbitals equals the total number of functions in the atomic orbital basis set. So when we run this, we can see that we get 1, 2, 3, 4, 8, 9, 10, 11, 12, 13, 14, 15, 16. So we have 16 basis functions, so we have 16 resulting orbitals. Well, we don't need all of those because remember, we had 22 electrons and 2 electrons can live in an orbital. So that means we need the 11 highest occupied. So we start with HOMO, the highest occupied molecular orbital, and then count down. And here we go. We can just run, and the pictures are already here, but we get those 11 molecular orbitals back out. And what we're seeing is that you're looking at the molecule with its orbitals plotted right on top of it. And that's lovely. And now we've got the energies. Well, with those two combined, we can look at a molecular orbital diagram, which is a way to understand what's going on in a molecule. So let me walk you through this. And I should show the code for this is not hard. We rearrange the energies and grab the ones that we want. Then we gather them using a numeric criterion to figure out which ones are degenerate, meaning that they have the same energy but different shapes. And then we put it together in some sort of, I did a tab view, but I just group them together. So what we're looking at is the lowest energy orbitals down here are the 2 oxygen 1s orbitals. And so those have the same energy as you would expect. And there's the in-phase combination and the out-of-phase combination. Then we get the carbon 1s orbital. And then above that, that's where things start getting interesting. We get the lone pairs on the oxygen. There's one here and one here. They're very low in energy. And then the next thing that we get are a sigma bond, a set of pi bonds, the other sigma bond. Remember, there are a total of 4 bonds. So 1, 2, 3, 4. There's the bonds for the 2 carbon double bond oxygen bonds. And then up here are the other lone pairs. And you might say, well, how do you know that? Well, again, that's a separate course on molecular orbital theory that I'd be happy to give, but not today. But what is interesting is to look at this quantum view versus the Lewis dot structure. So the Lewis dot structure still shows the bonds and that you've got these lone pairs, but what is elided here in this picture and this representation of the bonding is that these 2 pairs of electrons on either oxygen might, intrinsically seem to be the same, but they're not. They're a vast energy difference, and their shape is completely different. And that's the added layer of information that you can get by doing quantum results that you couldn't do with just a classical picture that the Lewis structures are based on. And this is really going to open up a lot of chemistry because the shapes of these orbitals and their energies dictate reaction possibilities. So without further ado, there are other talks from the chemistry group. So Jason and Sarah talked earlier. I'm talking now, and then later we have Sutik at 1, Bob is at 1:30, and then John will be talking tomorrow. And John is from the Academic Integration Support Services, and he's been on the road with me talking about how to do prompting for both chemistry and physics. So please check these out. And there are useful links for chemistry. If you haven't seen it, we've updated our core areas site and links to just about everything we've got. Then there's the dilution calculator. If you're working with biology students to get turned around on this, check out this resource. And then we have our other resources both for students and teachers, and then just everything that we've got. Thank you for your time, and I'm happy to answer any questions that have been put in the Q&A. So we have a question, any use of virtual reality in these chemistry applications? You can take the molecules that we render from Molecule Plot 3D and you visualize that on a Google class or something like that. That's been done. I don't have an example of that here, though. Curious about Wolfram Alpha LLM-backed teaching assistant professors teaching at a large college chemistry class. Well, there's a variety of different ways you can use our tools, either through Wolfram GPT, if you don't have access to our software on your campus. The other thing is that we do have some LLM kit-backed tools that can plug in to other LLMs besides just OpenAI products. And I encourage you to either check out the webpage on that for the Notebook Assistant, or swing back to later today, I believe it's at 2:30, there's a chemistry meetup, and we can chat more details about that there. In working with the WSRP students, the biggest struggle that we had this year actually was that for those, we had many students that were doing computational chemistry in the traditional sense, running the quantum chemistry paclet. And we underestimated the need of compute resources for running the calculations. So they ended up doing parallel processing in the old-fashioned way on multiple computers and then combining the results. So the students weren't exactly used to that. Those of us that have been doing comp chem for a while are quite used to running on multiple computers and or supercomputers. And next summer, we'll have that sorted. So good questions. Anything else? If not, thank you very much and enjoy the rest of your conference.